समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. Okay, in the previous class, we looked at why we need to use certain materials and in particular composites. So in today's class, we'll primarily look at the constituents of the composite, primary constituents, because there could be other additives as well. We'll be looking at fibers and matrices, reasoning out what is their purpose, why are they there, and how they blend together with each other. But before that, we will just review what we mentioned about why we are using composites, because we also need to discuss what are the issues with using them and how we can overcome some of those issues or still survive along with those issues. So let me just bring this up fully. Yeah. So the primary reason we use composites, of course, is their relatively better specific properties compared to metals which were conventionally used, especially aluminum alloys, in terms of the specific strength, sigma U by rho, the specific stiffness, more so in a dynamic situation as a square root of E by rho, and most importantly, the deciding factor being in the stability-based design, the performance index being E by rho cube, because of their lower densities and rho appearing as a cube in the denominator here, that becomes a primary deciding factor over many of the conventional materials. Then we said that there is a tailorability aspect, both from a structural perspective as well as electrical, heat resistance, etc. And then in terms of the ability to fabricate it using various prefabricated or partly fabricated forms like prepregs, SMCs, BMCs, etc. And then we also said that in terms of polymer matrix composites, the thermal expansion coefficients are lower, and therefore the ability for dimensional stability even in the presence of temperature changes is pretty good. And then the additional advantage we get, especially in vibrating structures, is that there is a material damping coming from the polymer, which is higher than in most metals. And then, of course, there is a superior resistance to corrosion, fatigue, and damage. And mostly we are talking about polymer matrix composites here, but it's important that composites are not restricted to polymer matrices, but also include ceramic and metal matrices as well. So some of those things, for example, for metal matrices would be very similar to metal behavior, not some of these advantages that we are mentioning there may not carry over there. And in terms of damage tolerance, we're looking at the ability for it to retard crack growth because of the fibers bridging the cracks in the matrices, and also the larger fracture toughness that we discussed relative to a particular question that we had from one of the students as well. Now, coming to the disadvantages or the issues with composites that we need to deal with, and we are still willing to live with it and use composites because we have ways of overcoming these issues. The first one is what you see in this particular picture over here, that you see the Young's modulus in a particular direction, let's say the direction X, how it varies with respect to the transverse modulus of that particular composite, because composites are transversely isotropic in the sense that they have certain properties along the fiber direction and certain inferior properties perpendicular to the fiber direction. So in the plane which is perpendicular to the fiber direction, they are isotropic, which is what we call as transversely isotropic. So if you take E2 as the Young's modulus in the plane which is perpendicular to the fiber direction, so any direction in that particular plane, the Young's modulus will remain E2. Now, if you're looking at the Young's modulus along the fiber direction, that is fairly high. So it's 14 times, for example, for the carbon epoxy composite compared to the transverse Young's modulus. In the case of let's say glass epoxy, it's about 5 times, and in the case of boron aluminium, it's about close to 2 times the transverse modulus. That's the longitudinal modulus. But now if you go to directions which are you're trying to load not along the fiber direction anymore, but at a certain angle to the fiber direction, obviously you're going to have a reduction, and the ultimate reduction will happen when you are having it at the load at 90 degrees, where the fibers hardly contribute anything towards the modulus, and it's only the matrix which contributes towards the modulus. So since we are dividing by E2, that is basically turning out to be 1. That is basically unity at 90 degrees. In between, what happens is there is a monotonic drop in the stiffness value, and this is the situation with the strength as well. Whatever large strength you have in the longitudinal direction, that drops off as you go towards the 90-degree direction. So this is one of the issues if you are using just all the fibers in one particular direction. And usually when you're designing a structure, you know what are the dominant loads, and therefore not only the magnitudes of those loads but the directions of those loads as well. So since you know a priori the direction of the dominant load, you would tend to design your structure such that you put all or most of your fibers along that particular direction. But there can be off design loads, and most structures are not just having one particular load. They could have other types of loads as well, so which means that you will have to design for certain strength and stiffness in the other directions as well, which is why we typically go for a laminate construction instead of just having a single lamina, or stacking all laminas in the same direction. We tend to have them in different directions so that you take care of certain off design directions as well. So that's what we look at first. Again, in terms of the material behavior, there is a complexity. One is the anisotropy that we just mentioned, that this directional behavior, it behaves in one particular way along the fiber direction, and another different way in the perpendicular direction, and in between there is a particular combination of these two which is happening. So therefore this anisotropy brings in certain complexity. The second complexity is because of its non-homogeneity. That is, unlike a metal, even if it is an alloy, point to point the properties remain the same, whereas within a composite, when you're moving from one point to another, so you might be at a point which is a matrix, suddenly you move to a point which is a fiber, then obviously the properties are going to be different. So that non-homogeneity has to be taken into consideration as well. All of this make not only the theory but even the experiments associated with composites, the fabrication of the specimen as well as the testing, all of which can be more complicated compared to testing a metallic specimen or analyzing a metallic specimen. What that eventually boils down to is in terms of the design cost as well as the design time going up, and sometimes substantially. In fact, we have numbers from Airbus for their design of the Airbus A350 extra wide body aircraft, where they showcase that just because they had to move from a conventional design to a composite design, the amount of time, extra time and extra cost that incurred. Of course, it happens to a larger extent when you're doing it for the first time in an aircraft in a large way. But as those technologies improve, these things come down. But nonetheless, compared to conventional material design, it will always be a slightly more. So therefore, the computational efficiency becomes even more critical when dealing with composites than when dealing with other conventional materials. The second issue, I think we discussed in the previous class also, a very good point brought out by one of the students, is that you would see that the leading edge is typically in many aircrafts, even though it might be the whole wing might be made out of composite, the leading edge might have a metallic component or a covering, which is basically because of the impact susceptibility of composites, because the leading edge is most susceptible to impacts, and therefore you would want to protect it, because as I mentioned in passing in the last class as well, these impacts can sometimes result in damages which in a metal can be visible, whereas in a composite can be invisible, because it could be an internal damage in one of the interior layers rather than the outer layer. Even though the impact itself has happened on the outer layer, the damage could have occurred in an interior layer, and unless you use non-destructive testing and evaluation, it might be difficult to find out that there is a damage until it becomes too risky. So this is an issue that we'll have to deal with, and one way, of course, as we saw, is to introduce that kind of covering with a metal. The other is to have a NDT NDE procedure, that is non-destructive testing and evaluation procedure, which is at a regular interval, so that you take care of this issue as well. The next thing is, of course, the fact that it has some of these composites, like especially Kevlar epoxy, which is basically an Aramid. Kevlar is an Aramid, but it has a particular trademark name by DuPont called Kevlar. So it's become very popular. It's something like many people are familiar with bureaus as a Godrej, because Godrej or locks as Godrej, or photocopying as Xerox, even though Xerox is just one particular company which does photocopying, but they were kind of pioneers, so you tend to associate that particular technology or that particular instrument or that particular verb itself with the company. So in the same way, when we say Aramid fibers, we typically refer to as Kevlar, but that's not the only Aramid fiber. There could be many other Aramid fibers. But the reason I brought that out is that that has a much higher fracture toughness, energy absorption capability in impact, so compared to other fibers like carbon fiber or glass fiber, etc. So you can use those to some extent in those regions where you know are much more highly susceptible to impact, rather than having a metal covering. The other issue is in terms of hydrothermal stresses, primarily more than the temperature, which may not be much of an issue with polymer matrix composites. It's the moisture. And many of these aircraft might be operating in high humid environments. Anyway, they are exposed to rain, etc., flying through clouds, etc. But in addition, there could be, let's say, fighter aircraft which are landing on, let's say, ship deck, which is in a highly not only moisturizing environment because of the high humidity associated with the waters of the ocean, but also the salt associated with that. And these moisture pickups by polymers, certain polymers more than the other polymers, can result in certain swelling, because of which there's a dimensional change, but more importantly, there is also a reduction in the performance in terms of some of the mechanical properties getting degraded because of the moisture absorption. So that's something that is of concern, and there are many different design changes that are done in order to accomplish that. We will look at some of them, time permitting, when we go a little more into detail on the hydrothermal stresses. The next thing, of course, when you're using especially thermoset polymers, which is what the industry has mostly been using, the aerospace industry in particular has been using certain grades of epoxies which are thermoset polymers as opposed to thermoplastic polymers. and there is a huge recycling issue. Unlike, let's say, your PET bottles, etc. So to some extent there can be a recyclability, but again, plastics in general have an issue with recyclability. But within plastics, the thermoplastics have a slightly better recyclability compared to thermoset polymers. So there is a trend in the recent years, for almost a decade now, very slowly, moving away from epoxies into some of the thermoplastic materials in order to address some of these issues associated especially with recycling. But there are other advantages as well going forward with thermoplastics. We'll come to some of that later in today's class. The other aspect is poor transverse properties, which we already discussed over here. Reduction of as much as 14 times you saw in the case of carbon, and in some other cases like boron aluminum, it just might be half. But that itself is a huge drop that you're looking at. So poor transverse properties is something that you have to live with. But as I said, by appropriate laminate design, the stacking sequence can be selected appropriately so that you can overcome this issue. It's not only poor transverse properties, but also shear properties. That's where the matrix comes into the contribution, because the transverse and shear direction properties, the fiber hardly contributes towards. It's the matrix which contributes towards. Therefore, by having better matrices or better quality matrices within epoxies itself, there are so many different epoxies, for example, you can address this concern to some extent, that there is a poor transverse and shear properties. And we say properties, we are primarily referring to the strengths and the stiffnesses in those directions, which is what needs to be taken care of. Another way of taking care of the poor shear properties is by having the fibers in plus or minus 45 degree directions, because once you have it in plus and minus 45 degree directions, along the fibers you are now having tension and compression because of the shear in this particular direction. We saw that in terms of the stress transformation when we discussed it in a previous class, where we saw that under torsion or pure shear, how it can be thought of as a pure compression in one direction and a pure tension in a perpendicular direction. Now if you put the fibers in those directions, you can actually handle transverse shear. So one way of handling transverse shear is to have, apart from 0 degree fibers, you have 90 degree fibers. So if you have only lamina which are only 0 degrees and 90 degrees stacked in a particular way, whatever way they are stacked in, as long as all the layers are only having 0 degrees and 90 degrees, it's called a cross-ply laminate. Now, along with these 0 and 90, if you have a plus minus 45 as well, and appropriate ratios, which we'll go to later, we get what is known as a quasi-isotropic material. So it is neither fully anisotropic nor fully isotropic, somewhat behaves like a isotropic material, which is what the word quasi means, almost. So quasi-isotropic laminate, when you have not only 0 and 90, but also plus and minus 45 in an appropriate ordering fashion, which we'll go to in a later class. Something like that, for example, a quasi-isotropic laminate which has plus minus 45 and 090, that's the simplest design. You can go for multiple layers where you do not need let's say 45, but you can do with 30, 60s, etc. as you go increasing the number of layers. For now, let's avoid those complications, but once you have a quasi-isotropic laminate, that takes care of this particular issue to a large extent, because now there's no such thing as a transverse direction and shear can be handled as well. So even though all of these are issues, design ingenuity and the ability of the composite to be tailored to a particular design has helped in avoiding or at least relegating many of these issues. So as I said, this poor transverse and shear properties overcome by a proper laminate design. Then another issue, the last issue that we'll be considering over here amongst the major issues is that whereas if you take one particular metallic alloy, let's say aluminium 2024, if you take two lots of that, you would get slight variation in property because of probably the manufacturing technologies and also the alloying elements varying slightly, or the crystalline structure slightly different in a statistical sense. But the variations would not be too much. If you plot a probability density distribution function, then the scatter or the standard deviations would be fairly small compared to the mean value of that particular property, be it Young's modulus or ultimate tensile strength or yield strength, etc. On the other hand, for composites, even leave alone two separate lots, from the same lot you make a specimen from one end of the lot and from the other end of the lot, you would see there is quite some difference in the Young's modulus along the longitudinal direction, quite some difference along of the strengths, etc. So we'll have to account for this, and one way, as I said, one of the earliest classes itself is to use a non-deterministic kind of an analysis where you allow for probability density distribution functions for each one of these quantities, be it the longitudinal modulus or longitudinal strength, in tension, again in compression, similarly in the transverse direction, the shear properties, etc. So we need to account for some of these things. And again, these properties could come because of the property differences in the fiber, property differences in the matrix, property differences in the volume fractions, the occurrence of voids. For example, while you are making the composite, there could be certain small air pockets which are arising. Those voids can create certain reduction in the performance and inferior mechanical properties like strength and stiffness. So all of these things need to be accounted for. And in parallel, of course, the manufacturing technologies are also improving so that the amount of porosity that you have, that is the void volume fraction, can also be reduced in many of the autoclave procedures or the vacuum assisted resin transfer molding, etc. When appropriately done, that can to a large extent reduce that. But fibers and matrices are not the only components. Sometimes you might have purposely add certain additives, but we'll go to that later, because the primary two components are the fiber and the matrix, and sometimes you have to allocate something for the void, so that for all practical purposes, if you add these three volume fractions, that is the fiber volume fraction, the matrix volume fraction, and the void volume fraction, you should get unity unless certain additives are added in a large quantity. Now let's look at what these composites are. So that's what we will do, because even alloys are consisting of more than one material. For example, if you take a titanium alloy like Ti6Al4V, it means that there is a certain percentage of aluminium there, indicated by those numbers that you have there, and certain percentage of the vanadium over there. So at least you have three materials over there. Apart from the major material titanium, you have two additional materials. So what is the difference between such mixtures that alloys are, for example, and composite, which is also a mixture? The main difference is that the mixture now is at a much more macroscopic level. It's not at very small length scales. It's at a reasonably larger length scale of the order of a few microns that we are talking about over here. So once again, these two materials are chemically distinct, that is the fiber and the matrix, and they are distinctly visible in a macro scale. So that is basically, again, it's a loose definition, because we're not saying what is a macro scale, what is exactly that number, etc. It varies from material to material in terms of the diameters of the fibers involved. So you can say it's of the order of magnitude of the diameter of a fiber, which for carbon fibers could be less than 10 microns. Some other fibers which are typically coated fibers like boron or silicon carbide, etc., it could be much more. But definitely much lesser than about 100 microns is typically what we are dealing with in aerospace grade composite fibers. Now, in addition, those constituents that you have, whether it is the fiber or the matrix, can come from one of these three categories, that is metals, polymers or ceramics. So if you look at structural materials in general, whether it is for flight vehicle application or for any civilian application like bridges, houses, buildings, etc., or automobiles, any structural material can be classified into these four categories. One is metals, polymers, ceramics, which are kind of very well understood for over a long period of time because they have certain behaviors. And then the fourth category being the composites, which is trying to combine these three materials. So doesn't mean it has to be one metal and the other one has to be either a polymer or ceramic. It doesn't need to be. Both could be metals. For example, you could have titanium fibers in an aluminum matrix. So both are metals, but it's a composite because one is a fiber, the other is a matrix, and these two are chemically distinct at a macro scale. And similarly, you could have a carbon-carbon composite where both the fiber and the matrix is carbon. So in a sense, a ceramic kind of a situation. But the most common being situations where you have the matrix as a polymer, and then the fiber could be ceramic fiber like glass or carbon, or it could be a polymer fiber like Aramid, or it could be a metal fiber like titanium, etc. So many different possibilities are there, but the idea is that each one of these categories as structural materials, metals, have certain advantages, like for example ductility, which is not there in the case of most polymers. Even thermoplastics, which offer a slight amount of ductility when you heat, they can be in a slightly liquid form but highly viscous, and therefore formability is not as good as with metals. Then ceramics, of course, not so highly brittle. So there are certain advantages associated with that. Again, in terms of using each one of these separately as a structure, primary load-bearing structures, because aerospace structures are pushed to the limit, polymers by themselves cannot be structural elements. But you see polymers used in secondary structures in many non-aerospace applications all by themselves. You see plastic bottles, plastic cans, etc. Some toys made out of plastics, which might be bearing loads to a certain extent, but not very high loads. So their strength and stiffness requirements are not too high. So polymers by themselves may not be used. Again, ceramics by themselves may not find many applications, but unless these are structures where impact is not at all an issue, and you can live with the brittleness, etc. So it's more often than not a combination across these things that we are looking at for composites, but need not necessarily be so. It's primarily just two chemically distinct constituents which can be chosen from any one or more of these three categories of metals, polymers and ceramics. The other important thing, we are still continuing the definition. Again, there are many different ways of defining it. So this is one particular way of defining it. So the first bullet point by itself does not define the composite. We are going further to understand what a composite is in terms of its a fuller definition now. Not only are those two materials chemically distinct on a macro scale, as we already mentioned, but the interface between that is between the fiber and the matrix, that interface that is there is very distinct. It's very clear, and many of the times you cannot just put the fiber as it is into the matrix, because the compatibility may not be good. So one of the ways in which you choose the matrix, as we shall see shortly, is based on the compatibility. You have chosen a particular fiber which is having enough strength and stiffness, etc., and low density for a particular application in an aerospace vehicle. Now you have to decide what matrix to go with it, and the primary consideration for that is of course the service temperature, but it cannot overrule an important thing, which is that these two materials, the fiber material and the matrix material, have to be compatible with each other. And sometimes sometimes we can live with incompatibility by bringing along a coating for the fiber. So we coat the fiber before it is put into the matrix material. For example, if you have, let's say, a silicon carbide fiber in a titanium alloy matrix, then if you just put it, then the interface will not be strong enough and it will become the weak link in the whole structure, and failures will initiate at the interface. So instead, what you would do is you would coat that silicon carbide fiber with a pure titanium metal, and then you put this pure titanium coated silicon carbide into the titanium alloy, and then it gels very well with the titanium alloy. So you will have certain distinct interfaces. Whether you have the coating or not, you can very clearly see in any inspection, especially through non-destructive evaluation, etc. You can very clearly make out there is this interface. And one is from an experimental point of view. When you're doing testing and failure occurs, you observe what has happened to the fiber, what has happened to the matrix. Not only that, but you also observe what has happened to the interface. Similarly, when you're doing an analysis, let's say using finite element analysis, etc., you typically introduce certain elements associated with the interface. So because that cohesion that is there, you have to bring in a certain cohesive law in order to account for that. So you bring in certain special elements associated with those interfaces, which have a certain combination of properties from the fiber and the matrix. So that's for more details. You can look at any of the finite element analysis courses later on. Now, the most popular such composite which satisfies all of these criteria is the fiber reinforced composite. So in other words, the reinforcement can need not necessarily be a fiber. It could be a particle. So you have particulate composites, for example, but which is quite commonly used in situations where cost is much more important. For example, in regular automobile manufacturing, secondary structures, etc. But for primary structures in aerospace, the most widely used kind of composite is a fiber reinforced composite. So the main part of today's class would be towards understanding why so. Why are we using fiber reinforced composites as opposed to any other reinforced composite? So since fiber reinforced composites are the dominant ones, we need to understand some of these mechanical properties of the fibers. Of course, these are improving over the years. This is about a decade or so earlier, where you look at some of the high performance fibers which are typically used in aerospace kind of constructions. The most commonly used is the carbon fiber. You can see the reason why in terms of the Young's modulus. You see you can go as high as 360 gigapascals. That is along the longitudinal direction. So this is just the fiber that we are looking at, not introducing the matrix yet. So whereas within carbon itself, depending upon how it is manufactured, because the raw material from which it is manufactured is usually a petroleum based side product or byproduct, petroleum industries byproducts, like it could be rayon, it could be pitch, or it could be a pan, what we call as a precursor. So in other words, it's something that is before the carbon is made. So there are certain processes involving heat treatment, etc., where from a pitch precursor or a pan precursor, which is pan being polyacrylonitrile, so you have or a rayon. So, and this is a very, very advanced technology, highly intellectual property protected, lots of patents associated with this. Very few companies produce this, most of them being in the US and Japan, and a few other subsidiaries of them in a few other countries. India has started making carbon fibers. NAL made made, the National Aerospace Labs did a pioneering work in terms of developing the technology and transferring it to various industries, Reliance, Adani, etc., do to some certain extent now. But you see that within carbon itself, there can be many different types. And as you increase the carbonization levels, in other words, the percentage of carbon that is there, you in certain terminology, you stop calling them as carbon fibers, you start calling them as graphite fibers. But the basic idea is the majority element there is carbon, and depending upon what is the precursor, what is the procedure through which you have arrived at it, what is the filament count, that is, you don't have just a single fiber. You typically have a bunch of fibers which are called as a tow or a filament. All of these are put together. You can have a roving, and then these in turn are put into a semi-wet matrix, which is basically what you call as the pre-preg. Right now we are focusing just on the fiber, and within the fiber there can be so much of variety within the carbon fiber itself. If certain materials are dominated by a stiffness design or a stability design rather than a strength design, then you would go for something which is a high modulus kind of a fiber. But of course, the determining factor would not be the absolute stiffness, but the specific performance index that we derive, that is square root of E by rho for stiffness, dynamic performance, or it could be just E by rho if it's a purely static deformation governed one, or E by rho cube if it's a primarily stability governed one. But in most cases, you would see that those are the situations where because you see the density is not different amongst these. There can be in a third decimal place or whatever there can be, but all of these three are having about 1.8 as the relative density. That is 1800 kilogram per meter cube is the density that you're having for these. So because density is not different, if the other only determining factor for the specific performance index, whether it is in stability or in the case of stiffness, including natural frequency dynamics, you see that this E alone determines, and therefore a larger E would be better, and therefore something like the HMS, which Hercules being the company which makes it, Toray being a Japanese company which makes it, etc. So Amoco is another company in US which makes carbon fibers in large scales. So if you're primarily interested in a stiffness or a stability based design, you would choose this carbon fiber, whereas if you're interested more in the strength, you would see that a particular fiber which has high modulus is actually having very low or relatively compared to the other carbon fibers is having a lower strength. The ultimate tensile strength is what we are looking at in the longitudinal direction. So all of these, when we say strength, we have to be very, very careful in qualifying it. We are talking of which direction strength, longitudinal strength. Again, in longitudinal strength, is it a tensile strength or a compressive strength? Of course, that difference is there even in metals, not only in composites. Between tensile and compressive strengths, there could be quite a difference. So we have to be very, very careful. So when we are talking of sigma U here, we are talking of the ultimate strength. Again, for metals also we have to talk of whether it's a yield strength or the ultimate strength, etc. Now here most of these are brittle. Yeah. Yes, please.
This is Vignesh.
Yes, Vignesh.
One question. Yeah, this sigma U is in this table. Is it what is it? Is it the compressive or the tensile?
It is tensile.
It's a hysteresis curve, right? It's the tensile in the.
Yeah, here, see, here we are only looking at fiber. We have not yet gone into the composite, and fibers cannot take compression. It's like our hair. You can stretch it. It can take a substantial load, but when you compress it, you see that it is, you can hardly take any compressive load. So here we are not really bothered so much about the compressive strength, because the compressive strength as well as the transverse shear strength are all given by the matrix. So right now we are focusing on the fiber, and its most important property we are looking at is the longitudinal direction tensile properties. So whether it is E or sigma U, both of them we are looking at longitudinal tensile properties.
So one second, because carbon, the Hercules HMS carbon has a modulus of 360.
Correct.
And the boron has a modulus of 385.
Very correct, yeah.
And both their densities, if you see, it's 1.8 for carbon.
Yeah, but boron is 2.65.
2.65.
Yeah.
Whereas you see the ultimate strength being 3.5 GPa for boron and just 2.2
Yeah.
for carbon.
Correct.
So these two seems to be the competitors for each other, right?
That's correct. Absolutely. But once the density becomes important in a, for example, in a criteria like E by rho cube or square root of E by rho, you will see that the carbon wins hands down. Whereas when you're looking at it purely in absolute terms, yes, this is important. But again, I'll also like to qualify it by saying that right now you're looking at only fibers, and you cannot have only fibers. You have to have matrix, and then the rule of mixtures or volume fractions comes into picture at the least to degrade some of these properties depending upon the matrix you're using. So you may not use a boron epoxy matrix, you might whereas you might use a carbon epoxy. Boron you might use with aluminium usually as a matrix, and aluminium will have a higher density compared to the epoxy matrix here. So not only is there a penalty coming from using the higher density boron fiber, but also the associated matrix which is compatible and which might be relevant for a particular application in terms of the service temperatures when you want to use boron, makes it even more of a penalty from a density point of view if that design is more associated with stability especially, but to some extent with respect to stiffness as well. But if you're looking purely from the absolute point of view and density is not critical, where you are absolutely right that these two are competitors, Hercules, HMS, and the specific boron fiber that is listed over here. And if both stiffness and strength are important in a particular design, equally important, let us say, then boron wins over compared to that. But it's subject to all those catches that I already mentioned.
Thank you, sir.
You're welcome, Vignesh. I think there was some other question.
Hello, sir. Good morning. This is Samanway.
Yes,
sir,
Samanway.
you told fibers can't take compressive loads.
Yeah.
Okay. And sir, in your previous statement, you told we tend to make the fibers at -45 and +45, and in that case, fibers are under in both tension and compression, so that they can take the transverse as well as shear loads. So if fibers can't take compressive loads, then why 45 and -45 we put?
Excellent question. Yeah, very thoughtful of you to have thought about that. See, when I'm talking about ±45, again, I'm not talking about just fibers alone. That is with the matrix. So the matrix is the one which will take the dominant load over there, and the reason why you need fibers along even the compression direction is because most of these loads are cyclic loads, and for some time this fiber might be undergoing tension and this fiber might be undergoing compression, but then it changes, and then this fiber undergoes tension and this fiber undergoes compression. For example, you can think of the torsional load. So if the torsion is in this direction, one of them will be under tension, the other will be under compression. But if the torsion direction changes, then what happens is you will have the vice versa. The one which was undergoing tension now undergoes compression. So you have to be prepared for both these regimes of operation, either in different parts of the flight mission that you are talking about, or it could be during a particular mission itself because of the dynamic loads which are vibratory in nature and therefore changing signs. Does that answer? And of course, the other thing is that it's not just fibers alone we are talking about. The matrix is also there. So the matrix offers substantial compressive strength over and above what the fiber itself does. And once the fiber is within the matrix, because it is held in place, now it has a certain amount of compressive strength that it can offer as well, in addition to that of the fiber itself. But the fiber by itself is having very, very poor thing, because it's not being held in place. That is the primary reason why its performance in compression is so poor when it is separate. It's like between, you would have studied plate theory and membrane theory. A plate is reasonably good at taking bending loads, but a membrane has ideally zero bending stiffness or very, very low bending stiffness, and therefore it's very easy to flex it, right? So it's similar to that we are talking about in a one-dimensional sense. That's a two-dimensional difference between a plate and a membrane. Now we are talking about a fiber and a rod, for example. So you have a rod which has a substantial compressive strength and bending strength also, because bending is something you get a strength only when you have both the tensile strength and compressive strength, because bending is going to be resisted partly by tension and partly by compression. So even if one of them is good, it's good in tension but it's not good in compression, then it's not good in bending. So that is basically the idea, and that's the reason why fibers are neither good in compression nor in bending nor in shear, but they are very good in tension. And so we are using our ingenuity in order to have all these different directions and use it along with another material, which is the matrix, in order to accomplish certain things which fiber by itself cannot do. But we still want to take advantage of the phenomenally large tensile longitudinal properties that it has, both in terms of the Young's modulus as well as the ultimate strengths.
Yes, sir. Thank you, sir.
You're welcome, Saman bhai. Anybody else have any questions? Okay, let me talk about the few other fibers that are listed over here. It's not just carbon fiber, which is predominantly used for very high performance primary load bearing elements within the flight vehicle structure, but even flight vehicles use the other fibers as well in certain areas. For example, glass fibers. Again, there are many different categories of glass fibers. Carbon also, here I've listed just 3 from the book, just for a sample. There are like hundreds of different varieties of carbon fibers that you can find of varying Young's moduli and strengths and the filament count, etc. Okay. All again based on which company is making it, like Hercules, Torre, etc. What is the precursor rayon, pitch or pan, and also in terms of the filament counts, etc. So various things come into picture in order to and what is the diameter to which you're going for an individual carbon fiber. That to a large extent determines the properties as well. So we will see the reason for some of those things in today's class itself. Apart from this category of carbon fibers, which are at the highest level of performance predominantly, the other very commonly used one is the glass fiber. And again, within that you can have many different varieties, again depending upon the manufacturer, manufacturing process, etc. and the content in glass. Glass is basically nothing but an amorphous material, mostly silica based, but not necessarily silica based, but silica would be a primary component there. So as opposed to many of these metals, etc., being crystalline structures, you have an amorphous structure, basically a random kind of a structure, which is what is glass. And there the two primary things that are used are E glass and S glass, E standing for electrical and S standing for structural. And you can very clearly see from the very meaning, electrical doesn't need to have very high Young's modulus or very high strength, but the structural glass is what fiber is what has relatively speaking between the two glasses higher Young's modulus of 85 gigapascals as opposed to 77 gigapascals for E glass. Similarly, here there is a substantial increase in going from E glass to S glass, from 2.5 gigapascals to about 3.5 gigapascals in the ultimate tensile strength in the longitudinal direction for these fibers. Again, if you look at the densities, there's not too much of a variation. Here it was all equal, 1.8. Here you're looking at 2.54 to 2.48. It's a small drop in going to S glass, because primarily you want to increase the strength and stiffness. At the same time, you want to reduce the density so that you have even better specific properties than the absolute quantities ratio. So that is basically what it is. Again, within S glass there can be a lot of varieties, etc. Once again, we are talking remember always pure fibers here without the matrix, which cannot be used in any structure. It has to be used unless you, let's say, have a truss-like structure, a cable bridge, etc., where you have only tension, is the only load which is occurring, and therefore you can use a bunch of fibers. But that's also quite rare. So you would, because you want environmental protection, etc., various other functionalities of the matrix will come into play. But because most structures are not going to be such that the fiber sometimes can experience loads other than tension, therefore you cannot use them only as pure fibers. You have to use them along with the matrix. Another very commonly used one is the Aramid. As I said, again, DuPont has a lot of patents towards that, and therefore calls that Aramid fiber, which is a polymer fiber, as opposed to these two, which are more ceramic fibers. Here you're talking about a polymer fiber which can go into a polymer matrix like epoxy. So it's by a polymer by itself is structurally very weak, both in terms of its strength as well as it is stiffnesses are very low, so you cannot use. But a polymer fiber in a polymer matrix is something that you can use as a composite, and it is used in many different aerospace application, even primary load bearing structures. And there are two types. One is the Kevlar 29, the Kevlar 49. Again, you can see a difference, not much in the strength, but more in terms of the modulus. The higher this particular number over there, the larger the modulus that is associated with that. So you have 130 gigapascals over here for Kevlar 49 as opposed to just 65 for the Kevlar 29. Once again, the densities are equal to each other and even lesser than the carbon fiber. So it's an even lighter fiber compared to the carbon fiber. But of course, you're having some sacrifice as far as the stiffness is concerned. But in terms of the strength, it is comparable with some of the fibers that you have, like especially the high modulus fibers. It's actually more than that. You're looking at, of course, a reduction in the modulus as the price that you're paying in order to go for that. But the reason why this is used in many applications is the impact susceptibility of composites, especially carbon fibers, glass fibers, etc. They're not very good at impact resistance, but Kevlar is reasonably much better than these in terms of the energy absorption capabilities and impact. And that's the reason, though it has lower Young's modulus and to some extent lower strength compared to the higher strength carbon fibers, you still go ahead and use them where impact is the primary concern. For example, in the containment rings, modern day containment rings, because previous day containment rings were all made out of titanium alloys, metals basically, but the containment rings in aircraft engines these days are made out of Kevlar as well. Dry fabrics. I was telling that very rarely you use fabric, the fiber alone, but if you weave that fiber into a fabric kind of a thing, it becomes a basket kind of a thing, and that can take certain impact loads. It's basically absorbing. You would see in, for example, you go to malls and all, you see those nets which are put if somebody falls to basically hold or to avoid large impact damage. So you see it's basically a netted kind of a structure at much more closer intervals. The pitch involved is much smaller, so you have these fabrics, and many of these prepregs may not have just fibers unidirectional. There are unidirectional composites also, but some of them can have woven fabrics, and again the kind of weave might be many different kinds of weave, the simplest being the plain weave, 2D. Again, there can be 3D weaving. Within 2D there can be many different techniques of weaving, satin, etc. So that's beyond the scope of this particular class. When you do the analysis and design of composites course, you would see more details of that. So you can use such a fabric as a structure which is primarily designed to take impact loads. Again, it cannot take any bending, it cannot take any compression, but the impact load that is coming is basically creating predominantly tension along the plane or the surface of the fabric, and therefore that is able to take that load to a large extent. Then coming to the one thing that we left out, silicon carbide. Silicon carbide fibers are typically used along with matrices which can also resist high temperatures like themselves, for especially for engine applications, but any other high temperature applications, let's say re-entry vehicles, etc. So this is having, let's say, Young's modulus somewhere in between that of the glass fiber and the carbon fiber, and also the Young's modulus, so the ultimate tensile strength is also kind of comparable with them, but its density is more close to the glass fiber density. So compared to the carbon fiber, it is heavier because it's actually a carbon fiber with a silicon carbide coating. That's what most silicon carbide fibers are eventually, and so that is something that you have to look at as the primary difference. But when like for example, when we are considering metals also, we looked at the three primary categories which were useful for aerospace applications: the steels and aluminum alloys, and in between the titanium alloys. So this is the titanium alloy is usually chosen, though it is in between these two, it's usually you don't choose those two extremes and instead choose a titanium alloy, especially when high temperature applications are involved. So silicon carbide is something like that. Again, as I mentioned in a previous class, getting that is very difficult because of the large amount of patents, etc., that are involved with that. Are there any questions related to these fibers and their mechanical properties before I move on? Okay. So these fiber materials, yes.
Hello, sir.
Yeah.
Sir, out of these fibers, which are ductile and which are brittle in nature?
Yeah. So see, all of these, it depends on the material that is involved. You just go back to the original classification of what they were, whether it is a polymer, whether it is a ceramic, or it is a metal, right? So, for example, this Kevlar is an Aramid fiber, so that is having a certain level of ductility, and which is what is actually enabling its higher energy absorption also because of the ductile deformation. It's one more important property that I missed out giving over here is the failure strain, because that is another critical property which is what determines the ductility. Glad that you brought that point out, because it doesn't come purely from a Young's modulus or the ultimate tensile strength or a rho, but a higher failure strength, and so it should have a certain plastic regime where it is going from an yield kind of situation, may not be exactly in the yielding in a metallic sense, but in a certain sense like that. So this to some extent has, but most of the others are all ceramics that are involved, and they are quite brittle, so their ductility is pretty low. But once you draw them into a fiber form, compared to their bulk behavior, there is a slight improvement in the ductility, but still not as good as metals, for example. So when you have a metal fiber in a metal matrix, for example, a titanium and aluminum kind of a composite, you have both the fiber and the matrix having very large ductility. But even though these fibers, the top few, are all predominantly brittle, you are still willing to live with it, because the matrix that you're having, again, the matrix most cases is epoxy, and that's a thermoset matrix which is also brittle, but the strengths are so high that you're willing to live with it to that particular extent if the the energy absorption capabilities or impact is not a predominant problem. But then you mix it with certain other hybridization with some other materials which can take the impact loads if they are going to be there, but not the dominant loads. So does that answer your question in terms of the relative comparison of the ductility or brittle nature?
Yes, sir.
Yeah.
Sir, then one more thing. So once the composite is made out of these fibers, then they are mostly brittle in nature, we can say. I mean, ductility is not that high.
Yeah. If you're looking at, typically when we say composite, unless otherwise specified, we are talking of fiber reinforced plastics. FRPs, as they are abbreviated. But as I said, it need not always be a plastic. It could be a metal or a ceramic also. And if it is a metal, then it will the matrix is a metal, that is. Then you are having actually a ductile composite. But most cases, as you rightly pointed out, it's a polymer. And within polymers, there is thermoset and thermoplastic. Thermoplastic, to some extent, it has a certain level of I can't really call it ductility, but it's less brittle, we can say, compared to thermoset polymers. So in that sense, you have a certain regime to certain levels of temperatures. You can have a partially liquid kind of a state, very highly viscous, but difficult to work with, unlike a thermoset. But you can do that. So many of the things that you're looking at now, like peak, for example, polyether ether ketone instead of the epoxies which are conventionally used. So then you can improve the ductility to some extent. But we are still willing to live with it because, see, ductility is important from two perspectives. One is in terms of the energy absorption, etc. The other is more important thing is in terms of shaping a structure, making a particular component in many complicated shapes that are required for the flight vehicle structure. The airfoil shape, etc., even with inside in terms of a T cross section, channel cross section with the appropriate chamfers, etc. But you know that these are available in the form of prepregs, which is a semi-wet kind of a situation. So you can actually shape it into a particular thing in that wet state and then cure it. Because once it is cured, it becomes quite brittle. So you cannot shape it further. Though certain machining techniques, etc., are still used, there are ways in which they have been, those technologies have improved as well, but not as good as metals in terms of their ductility. So the reason, for example, you are able to drill a hole in a metal is because, or even let's say shave off material in terms of machining in various forms, is because at the region where the material is being removed, the high temperatures result in almost a liquefied or a plastic state of the material, which is what enables such machining, which is much more difficult in a brittler composite. Does that answer your question? Yeah.
Yes, sir. Yes, that answers my question. So then one more thing, since these are predominantly brittle in nature, mostly the composites under operational conditions, they will be under multi-axial load.
Yeah.
So then if we want to measure the failure, then this Born-Mises stress criterion, all this Tresca yield criterion, this will not be valid in these cases.
That's correct. Very good point you brought about. We will look at all those failure criteria later on, but just to briefly answer your question over here, there are generalized versions of those. See, it's not that they're not completely inapplicable, but you can kind of generalize them to see what is the takeaway from them. But as long as there are things which are associated with the yield strength, for example, there's no such thing here. So obviously there you can't directly take them over here. Any failure criteria or strength criteria which is associated with an yield strength, for example, cannot be directly adapted over here. But there are certain ways in which you go about. The other complication that you brought about is in terms of the multi-axial loading. Very good point again, because you're designing not only for loads in a particular direction, but in multiple directions. But a priori, we know which are the dominant directions. So we tend to have more fibers along, or more layers of fibers having the fibers along that direction in which the load is. Even in a multi-loaded situation, it's not all the loads in all the directions are going to be of the same orders of magnitude or same magnitudes. There is going to be a difference. And so certain directions can be designed for lesser strength and stiffness, and it's still okay compared to certain other directions, because you know that loads will come in those directions as well, but they will not be as high as the loads that are coming in the primary loading direction, which is what you're designing most of the fibers to be along. Yeah.
Right, sir. Actually, sir, I brought up this question because in RCC beams and columns, the fibers are reinforcement bars, and they are actually ductile in nature.
Right.
So, while analyzing those structures, we use this von Mises criteria a lot actually. So I was thinking about
very good. It's an excellent question. See, in fact, these are all experimental based failure criteria. You test the material and then you come up with certain strengths, etc., and then you develop it. And when it's a multi-axial kind of a situation, you will have what are known as failure envelopes, where when both the loads are present, failure can occur when neither of those loads have reached their own ultimate or even yield levels. So that is basically what that kind of a situation is. So though there are lots of failure criteria for composites, extending some of those, like what we call as the Sai-Wu criteria, Sai-Wu-Han criteria, etc., some of which we will visit later on, but none of those are actually accounting for the actual behavior of the composite, and that's why there was something called the worldwide failure exercise in composites, conducted over a decade or more in 3 different phases, and each one of them was a blind challenge thrown to some of the topmost brilliant brains working in the field of composites in terms of propounding certain failure theories, and for blind test data, certain parts of the test data were given to them, certain parts were concealed from them purposely, and then they were asked to make certain predictions, and then in the next phase, those data which were concealed were also shared with them so that they could improve upon their models. See, eventually it becomes like curve fitting. So you're trying to improve it based on the curve fitting, and that is acceptable where you do not have what are called as phenomenological models. That is the ultimate, a physics-based model where you understand the physics that is happening at the damage level, because the damage mechanics is highly complicated here. There can be a damage either in the fiber or in the matrix or in their interface, what we call as fiber breakage or fiber micro buckling. One of you asked a question about fibers not being able to take compression, but once the fiber is within the matrix, it is sharing the compressive load along with the matrix, because the matrix is holding the fiber along that direction. It doesn't allow it to bend so easily. But still, once the compressive load goes beyond a certain point, some of the fibers can undergo buckling. That is called micro buckling, fiber micro buckling. So some of these things can occur with the fiber. Then you could have matrix cracking, then the fiber matrix debonding, then between layers delamination occurring. So many complications are there. We have to understand, if we really want to understand the damage mechanics and come up with a failure criteria like what you're talking about, whether it's Tresca or von Mises for metals. If you want to arrive at here, there is a lot of thought which needs to be given to the behavior of the fiber, behavior of the matrix independently, and then as a combination along with the interface, and understand the physics that is going on. Still, a lot of empirics is involved in terms of the testing and getting the testing data. There are very complex equipment which are able to test a fiber alone, or even smaller diameters like carbon nanotube, which has even of the order of nanometers is the diameter instead of microns that we are talking of for a carbon fiber. You can test that. So there are ways in which you can gather data from that, etc. So there's a whole lot of improvement that is happening in the experimental technologies as well, because many of these things still cannot be explained purely through physics. Our understanding of physics at very high speeds, that is relativistic physics, and again at very small dimensions, which is basically at nanometers or lesser angstroms, etc., is very, very minimal compared to our understanding of continua. So the continuum mechanics has been around for a long period of time. We have understood it fairly well. Vignesh, for example, your teaching assistant, is working on molecular dynamics. We are looking at the molecular level how it behaves. There are people looking at the atomic level and subatomic levels also what is happening. So those are the things which are going to give us insights into the behavior of the physics, because we have to build this up at various length scales. But it's kind of an overkill when you're doing an aircraft structural analysis to do molecular dynamics, for example, because you can get reasonably good results even with a continuum model. So it's only when you're trying to understand these failures and trying to improve upon the material itself, better and better materials which will fail at a much higher load or will deform much lesser, or for certain applications be more flexible, etc., without failing. So that is very large failure strain involved, etc. Then you have to go for what are known as phenomenological models. That is, you understand the phenomena behind this damage. So suppose a fiber microbuckling has happened, why it has happened, what is the geometry associated with that. If it's a fiber breakage, what is the material physics associated with that, and then incorporate that into the understanding of the mathematical model, the damage model, and then all of them put together, you basically come up with the overall composite representative volume element, which is an equivalent homogenized kind of material, imaginary material, how that behaves vis-a-vis the actual composite, and based on that come up with certain failure envelopes, which will be useful then for a design, because each time you cannot go to these lower levels in order to understand. From these lower levels we try to understand the physics, understand the phenomena, and come up with certain phenomenological model, which we then upgrade to the higher length scales, and at that length scale we try to apply it as if it were material which is imaginary material, fictitious material, that is, which behaves as a structural component. Overall it behaves same as that same component made out of the actual material in terms of fibers, matrices, and each layer being having fibers in different directions, etc. So you try to analyze that as an equivalent homogenized material which is anisotropic, having different properties in different directions. But this kind of a gradation is beyond the scope of this class, because you asked the question, I'm just trying to explain in a qualitative sense, but there's a lot of mathematics and physics that goes into understanding these at those levels. Is that clear?
Yes, sir. Thank you, sir.
Okay, you're welcome. Any other questions? Okay, so let me complete this slide. Fiber materials can be classified into two categories, the basic ones and the advanced ones. It's primarily based on the Young's modulus along the longitudinal direction in tension. That is what we had listed as E over here. So anything which is less than 100 gigapascals, like for example, here you have the E glass and S glass, which are 77 and 85 gigapascals, or one kind of Kevlar, which is Kevlar 29, which is 65 gigapascals, is the Young's modulus. So all of those would be classified as basic. So here I've given those two examples. It includes Kevlar 29 as well from this table. Apart from the fact that they are low modulus, the advantage of that is that it is low cost as well. Which just happens to be a coincidence, may not be a coincidence if we actually reason out the economics behind this whole thing. But the fact that they're low cost means that we can now use them in high volume applications, not in structural applications where modulus might be very important. But though a lot of light vehicle structures do use S-glass, even primary structures, like for example helicopter rotor blades, which is the most important primary structure in any helicopter, uses S-glass to a large extent. Though at certain locations it includes carbon fiber as well, but you can build helicopter rotor blades entirely out of S-glass as well. There's nothing precluding that. So high volume applications is where these find more of a room, and one such industry example is the automotive industry. We're not talking of the racing cars and etc. We're talking of the more generally available cars for the public to buy. On the other hand, those which are having larger than 100 gigapascals, in this case all the carbon, the Kevlar advanced version, which is 49, and also boron, silicon carbide, etc. These are all examples of advanced fibers which are very expensive and therefore used only in certain niche applications or exotic applications, as I call it here, which could be not just aerospace but also the sports industry. It's been a pioneer in using that. Bicycles, you have these golf rackets, you have the tennis rackets, golf clubs rather, sorry. So all of these high performance sporting equipment segment can be using many of these high modulus fibers because there the performance increase, even if it's by a smaller amount compared to going from glass to carbon, let us say, even if there is a slight performance index, we are willing to pay a higher cost, because the running cost in terms of trying to get back the revenues that are going to come out of it, or let's say if it's a military kind of an application, the kind of payoffs is a qualitative judgment that we make, that yes, we are willing to pay a higher cost in order to achieve even a small amount of increase in performance. And many a times it's not just a small amount of increase in performance, it could be a substantial increase in performance that you're getting as well, which could make do or die kind of a situation possible, whereas it may not be possible with a lower modulus or lower strength fiber. So is that clear? Yeah, this classification between basic and advanced. So let me next go into a more primary question, why fibers. Before that, we need to understand one more primary question at a much more fundamental level. What do we mean by a material property? Why do we call a particular property as a material property? Anybody?
Sir, because these properties do not change with the dimensions. These are constant.
Excellent. Very good. Yeah. So we can classify broadly properties into two kinds, so geometric properties and material properties. So those properties which do not vary with the geometry, which vary only when you change the material itself, are the ones which are called as material properties. Okay. So in that sense, if we take an example of the ultimate tensile strength, let's take a few examples. Young's modulus, we have looked at so many different things, density of the material, etc. So if you take a look at all of them, and then let's say we zero in on one particular quantity, let's say it could be the Young's modulus also, but for an example's sake, I'm taking the ultimate tensile strength. So is this ultimate tensile strength, usually expressed in gigapascals, is this a material property or a geometric property? It might sound like a silly question, but I have a purpose for asking that. Is this a material property or a geometric property?
So this is a material property.
Okay, let's have a quick vote. Let's say all of you who think it's a material property, type M in your chat box, and all of those who think it's a geometric property, type G, or who think it could be both, type GM. Let's see what kind of a count we have. I'm not looking at the chat box. Maybe Vignesh, you can look at that. Your time starts now. You can take about 10 seconds to type M, G, or GM. Okay, you don't need to have an exact count, but Vignesh, can you just tell me which is kind of dominating, whether it's the M or M's or the G's or GM's?
TMs at this moment.
Come again?
Yeah, it's TM there.
M,
Yeah.
okay. Okay.
M is dominating. There has been one GM, that's it.
Okay.
All are remaining are all M's.
Okay. Okay, very good.
Yeah.
Yeah.
GM, two GMs, yeah.
Okay.
Just two GMs on the way. Yeah, remaining are all M's.
Okay.
Just two GMs.
Okay. Okay. So either of you who answered as GM, can you explain to me what you mean by that?
Hello, contingency.
Come again? I couldn't hear you clearly.
Actually, Ranjan Patak, hello, contingency answered here.
Sir, Akshay this side.
Yeah.
The ultimate tensile strength will depend upon the direction also.
Okay.
In which direction we are taking it. How
Good.
the microstructure is elongated. If it's a
Okay.
roller section along the rolling direction, it will be different.
Very good.
Transverse direction, it will be different.
Excellent. Yeah. So it is directionally dependent. It's anisotropic, but let's leave that for now. Let's say we are talking of, when you say UTS, as I said, it's only in the longitudinal tensile direction. Okay. So only in longitudinal direction. only in the tensile loading. Okay, so then is it a material property or not, that particular UTS?
So then also it depends upon the cross section, how the cross section is, circular or square or trapezoid.
Very good. Yeah. Okay. Let's see what is that. And one more person answered that, right? What was his answer? Because I was not able to hear very clearly. Anybody heard that?
The loading condition may depend on the geometry, even in a simple case.
Okay.
So material property alone cannot define UTS.
No. I'm asking whether UTS along the longitudinal tensile direction is it a material property or a geometric property or both? That's all that I'm asking. Because we are fixing the direction, we are fixing the sign of the load also. It's positive, that is it's tensile, and it's along a particular direction. So we are not allowing for the change in direction. That's what we are defining as UTS for our purpose, for this slide purpose. Okay. So that UTS along the longitudinal direction in tension, is it a material property or a geometric property or both?
There should be a plain material property.
Okay. So fair enough. So most of you answered it's a material property. So the next question that arises from this exercise is, do material properties depend only on the chosen material, or they depend on the shape and the size of the object that you're testing also? See, how do we determine the UTS? You typically have a uniaxial testing machine, what you call as an UTM. You will see once you get back on campus, those of your MTech students, when you come back on campus, you will see you will be doing certain experimental testing as well. You would probably see that there is a UTM, and some of you might have already seen even in your BTech labs, etc. So you create a certain specimen and then you test that, and then you test it all the way to failure. And if it's a metal specimen and a tension, then the load at which it fails divided by the area of the cross section basically gives you the ultimate tensile strength. And if you do it for different cross sections, you'll still arrive at the same load, different load, but the same ultimate tensile strength. And that is what you're calling as a material property. So is this always true, is what we are asking here, that the material properties, in particular we are focused on UTS here, but for all practical reasons it could be the Young's modulus also, where you're plotting the stress versus strain even before failure, especially in the linear regime, and then getting the slope of that stress versus strain curve in tension along the longitudinal direction, and you're getting that slope as the Young's modulus, right? So now, do these material properties like E or UTS in a particular direction in tension depend only on the material of that specimen, or it also depends on the shape and size of that specimen that you're testing?
Sir, I guess it depends on the shape and size also, because while testing in the UTM, we'll have a standard shape. For example, testing in the UTM, you'll have a dog bone shape for the metals. So in order to, because we have standard shape testing in the material, so that's why I'm giving the answer that it depends on the geometric property also.
Okay. Good, fair enough. So there are very good point that you brought about in terms of the ASTM standards, etc. There are very clear definitions for the specimens to be tested in terms of their shape as well as their sizing, and your dog bone shape, as you said. The dog bone shape is more to ensure that the Saint Venant's principle comes into picture, that irrespective of the way you're applying that particular load, which is also defined in the testing standards, by the way, but irrespective of that, in the interior region where it is failing, actually where the stresses are larger, so you do not want that region where it is clamped, for example, to fail. You want the in-between portion, which is of a smaller cross section, to fail, because then that would be determining how the material behaves rather than how the boundary conditions are affecting it. So you want as less an effect of the boundary condition and as much an influence from the material, and therefore you're specifying a particular shape and size. But do you think by having a different shape and size, as long as you still have a dog bone, but let's say double both the outer edge as well as the inner edge, you're doubling the areas of cross section, would you think the UTS that you get out of it would be very different, the value?
No, sir.
For the same material?
No, sir. It will be same.
Yeah.
Yes, sir.
Geometry is increasing proportionally, then it doesn't matter.
Okay.
Sir, we take dog bone shape to determine tensile strength or maximum tensile strength of a material using STM standard. But when we write the result, is when you write the material property, even after testing, you don't need to specify that you have used this specimen or this dimension or that. Because I think whatever dimension you use, the behavior will be same.
Okay.
So it doesn't depends on shape and size.
Right, right. So the load at which it fails will depend upon the cross section, but the stress at which it fails still is approximately the same. Yes, you might have some minor variations, etc., for various reasons, but it's roundabout the same. Leaving out for some statistical variations, etc., you would get almost the same kind of thing, as long as you're taking care of the boundary conditions and the loading, etc., in an appropriate way when you're changing the dimensions. It is a material property, and therefore if you're making these two specimens of different geometries from the same material, so you should get around about approximately same values at which stress at which it fails. The load is different because the cross-sectional area is different, and you're going to divide the load anyway by the cross-sectional area. And of course, there are two things here. There's something called the true stress and the apparent stress, where you're either dividing by the nominal area, nominal stress, to get the nominal stress, which is the undeformed cross-sectional area, or at the point of failure, because there was a thinning down of the specimen, the cross-sectional area is reduced a bit, let's say. Now, Poisson's effect basically is taking over, and it has also gotten into the plastic regime, etc. So the stress can be much higher. The true stress can be much higher than what is predicted in terms of a nominal stress. But let's leave all those differences aside. We're talking everywhere purely in terms of one particular kind of stress. So that's not different in the two cases. Only the cross-section geometries are different. So shape or size or both are different. It should not change, right? The material properties should depend only on the material. That is what we understand by the fact that it's a material property. That's why we call it material property in the first place. So now, should the ultimate tensile strength, coming to the point that I'm trying to bring about through this whole exercise, should the ultimate tensile strength along the fiber direction in tension for a given material, let's say a particular carbon fiber, like the many examples that we saw. One example is, let's say, a T300 fiber, one particular manufacturer making a particular kind. So this ultimate tensile strength, should it depend upon the fiber diameter? So the same T300, I make it with two different diameters. Should the and it's a single fiber that I'm testing. I'm not testing a bunch of fibers, which is called as a toe or a roving, but I'm taking out a single strand of this fiber, and two fibers. One is of a lower diameter compared to the other one, which is a higher diameter. I'm testing these two until failure occurs. I know the failure load. Now I divide by the cross-sectional area of these two fibers, pi d squared by 4. In one case it is d1, the other case it is d2. Of course, the load is going to be different because the geometry is going to be different. But once I divide by the area to get the ultimate tensile strength, longitudinal tension, will it be the same or different?
Same, sir.
The same. So again, let's go for a vote. Again, let's go for a vote. Those who think it will be same, type S, and those who think it will be different, say type D. Yeah, Vignesh, can you now just check which is dominating, S or D?
Sir, Renuka here.
Yeah,
so
yes,
S is there are more votes for S.
Very good. Okay. So that's good. So from our discussion on material property, where we said that it is called a material property because it should depend only on the material. Therefore, it should not depend on the fiber diameter, which is a geometric property, right? So yes, that is fair enough from our understanding of material property now. So now, if I plot UTS versus fiber diameter, according to the majority opinion that we had, it's same. That is two different diameters we chose. That is, let's say one is D1 over here and another is D2 over here. So both those will lead to the same ultimate tensile strength. So in other words, if I plot for various fiber diameter, I should get a horizontal line. In other words, a line which is parallel to the x-axis or the fiber diameter axis. Let's say the fiber diameter is listed in microns over here. Okay. So now some of you did answer D, right? There were a few D's, right, Renuka?
Yes, sir, there were a few D's, 1 or 2.
Okay. So especially for those of you who have answered D, now there is another difference. Those of you who had answered S basically means that this is a choice that you made, B, that it is constant. But those who have made a choice that it is not the same, it is different, that is D. Now you have two different choices. Either it is monotonically increasing or monotonically decreasing, or neither of the above. It could be increasing and decreasing or decreasing, increasing, etc. So these are three choices, A, B, C, and a choice D, which is none of the above. Okay, so now let's go for another vote, A, B, C, or D. So those who said same can vote B. The rest of you who voted different, that is D, now you can vote A, C, or D. Okay, Renuka or anybody, can you just tell me what is dominating between A, C, and D? Forget B for now. Let's just look at between A, C, and D, which seems to be.
So C seems to be more.
Okay.
There are lots of B's and A is very less.
Okay. Okay.
None of them have voted for D.
Okay. Okay. Okay, some of you who voted A, any one of you, can you explain why it is monotonically increasing with fiber diameter?
Sir, Akshay is saying as the diameter reduces, the defects concerning size is reducing. We are reducing the dimensionality of the defects, like from the plates to...
Did you answer A or C? Did you answer A or A? Okay. So here... see that fiber diameter is increasing and you're saying that it is monotonically increasing with that.
No, sir, fiber diameter should be increasing.
Okay, so you just hold on. That means you meant to answer C, but you answered D, A by mistake. Okay. Anybody else who answered A, can you explain why you answered A?
Sir, I'm Ranjit George. I had also answered A, but I also thought that fiber diameter is decreasing as it goes on the x-axis.
Okay. So most of you who answered for the previous question as D, that is different, are now moving towards C, that is, it is monotonically decreasing, right? And what's your reason, George?
Sir, actually, I don't know the physical principle behind it, but I do know that we're going towards a trend of more of nanofibers, and I guess that's more to do with the matrix than to do with the fiber itself, but reducing the diameter does increase the strength
A very good point. What you're saying is, as you move towards the left end, that is, you're having lesser and lesser diameter, you're basically moving towards nanofibers, etc. And so, you are probably aware that carbon nanotubes, for example, have a higher strength in tension compared to carbon fibers, and therefore along the longitudinal direction, and therefore you're saying that when we go from right to left, it should increase, which is what I'm calling as monotonically decreasing along with the fiber diameter, right? So that is a very good point that you have brought about. I think we are running out of time, so we will probably revisit this problem from this stage. So what you have mentioned, even the previous student have mentioned in terms of defect, etc. That plays a very major role, and the kind of reasoning that you did in terms of going from examples of carbon fibers, carbon nanotubes, etc. is also a reasonable thing. But then if it's a material property, why should it depend upon this fiber diameter, which is actually it's actually a sizing? You're still talking of a circular cross section, so you're not changing the shape. Shape remains circular and long fiber, but still now you're looking at a situation where you're looking at larger diameters. So sizing is changed. So sizing is actually a geometric feature. So why does sizing actually affect a material property? Okay, so some hints you have already got from your classmates. Let's look at it from a little more rigorous way in the beginning of the next class. Thank you very much.
Thank you, sir.
You're welcome.
Thank you, sir.
Welcome. Yeah.
Thank you, sir.
Thank you, sir.
Most welcome.
Thank you, sir.
Thank you, sir.
मृत्युंजय मंत्राः
See you on Thursday.
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षेयमामृतात् ये ते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा